All right, let's get started with a problem now that involves three-component mass transport. We're going to start with an example where we have three gas components that are diffusing towards a catalytic surface, as shown here. And one of the components, A, can undergo reaction at the surface to form N molecules of B according to the reaction stoichiometry that's shown here. There is an inert component, C, that doesn't participate in the reaction, and the chemical reaction we're going to set to be irreversible and infinitely fast, in the sense that the mass transport is limited by flow through the boundary layer region next to the catalytic surface. So that will simplify the problem a little bit, but still allow us to readily bring in all of the effects of a third component on this process. And so we start out with a situation where the reactant A is present outside the boundary layer in a well-mixed layer at a concentration of XA0. The axis is set with Z being 0 being at the edge of the boundary layer. Beyond the boundary layer, compositions of all the components A, B, and C are constant, and within the boundary layer the concentration of A decreases down to the catalytic surface, where its concentration or its mole fraction is equal to 0, and the concentration of B, then the product of the reaction of course goes in the opposite fashion. I've drawn these concentration profiles as linear, and in the very simplest case that will be true, where there's no significant convection. However, understand that these are just drawn for convenience, and depending on the particular problem under consideration in the reaction stoichiometry, these concentration profiles may not necessarily be linear. And again, component C is an inert that does not participate in the chemical reaction, and its composition may, as you go from the edge of the boundary layer to the catalytic surface, may either rise or fall depending upon the reaction stoichiometry. We're going to see that, and depending on the diffusion coefficients of the components in here, and we'll see that as the solution gets developed. We're going to look at this in the limit where temperature and pressure are constant, and what that means is that and where the gases are ideal, and that means that the total molar concentration of gas inside this boundary layer is constant. Remember that for an ideal gas, the molar concentration is just the pressure divided by R, the gas constant, times temperature T. And so if temperature and pressure are constant, then the total molar concentration is constant as well. Because we're dealing with gases and the total molar concentration is constant, we will use molar units to solve this problem. One could also do it with in mass units, but you have to be a little more careful with with some of the assumptions related to the average convective or frame of reference velocity, and I'll go through that a bit later in the notes. And so we're going to start solving these problems from, as we saw a bit last time, but we'll see it again and again as we go forward. Now we will start to solve them using the continuity equation, the overall continuity equation, and the species continuity equation. And the idea here is to start from our general mass balance equations and then simplify them down to a case of particular interest. And typically the best place to start in solving these problems is to first use overall continuity equation to say something about the convective velocity, and in molar units that'll be the molar average velocity V star that's shown here. And we start with the overall continuity equation, and it tells us that the time rate of change of the total molar concentration plus the divergence of the product of the molar concentration and the molar average velocity has to equal the net rate of production by chemical reaction of each of the species in the gas phase. Now, the chemical reaction is occurring at Z equal delta. It's occurring at this surface. There is no chemical reaction occurring in the gas phase, so these terms on the right-hand side are equal to 0. We're going to solve this problem in the limit of steady state, and so the time derivative becomes 0. Also, the total molar concentration is constant, and so again that means it can't be changing either in space or in time. And because the total molar concentration is constant, we can take it outside the derivative and get the result that's shown here in equation 2. And we're considering one-dimensional diffusion, and so that the divergence of the velocity can be written as shown in equation 3. And what this means is that since the total molar concentration is not 0, it means that the molar average velocity, Vz star, cannot change in the z direction, or equivalently that Vz star is equal to a constant. And that's really all that we get from the overall continuity equation, is we get a statement that the molar average velocity in the z direction, and this will turn out to be related to the convective velocity or frame of reference correction term in the species mass balance, we get that velocity is equal to a constant. In order to evaluate what that constant is, we have to turn to jump mass balances at the catalytic surface, basically boundary conditions. So the boundary conditions of the problem will establish the exact value of this molar average velocity. And so we consider the solid catalyst to be phase 1 in this case, and the gas that's contiguous to it to be phase 2, and we write the jump mass balance in molar units as shown here. The catalytic surface is not moving, and so this interface velocity u is 0, and I can then applying the nomenclature or the meaning of these brackets, I evaluate the term in brackets in phase 1, that is the direction in which the unit normal at C is pointing, and then subtract from it its value in phase 2, or the gas phase in this case. And so I'd apply that the definition of these the bracketed term, and that's shown here, write out explicitly the net rate of reaction of each of the components. Component C is inert, and so at the catalytic surface and in the gas phase, its reaction rate is 0. At the catalytic surface, the rates of production and consumption of components B and A are related to one another through the stoichiometry. A goes to NB on that catalytic surface, and so that implies the relationship shown here between the net rate of consumption of A and the net rate of production of B. And so we can write this term only in terms of, for example, the rate of consumption of A and the stoichiometric coefficient N. There is no gas dissolved in this case in this catalyst, and so the concentration of gas in phase 1 is equal to 0, so this term goes away. The gas phase velocity at the surface of the catalyst is Vz star, so that what I'm labeling as Vz star superscript 2, that's the velocity in the z direction, molar average velocity in the z direction at the catalytic surface. That is equal to the molar average velocity throughout the gas phase, simply because the molar average velocity throughout the gas phase is a constant, and it is therefore equal to its value right at that catalytic surface. And so with this result, we can write the we can write the molar average velocity throughout the gas phase in terms of the molar average concentration, the stoichiometric coefficient, and the net rate of production of A, which is going to be at the catalytic surface, which is going to be a negative number since A is consumed at that surface. And what this says is that the molar average velocity, or the convective velocity if you will in this problem, is equal to 0 only when n, the stoichiometric coefficient, is equal to 1. And when n is equal to 1, this corresponds to a case where one molecule of A is transformed into one molecule of B. So for every molecule of A that diffuses to the surface, we have a molecule of B diffusing back out away from the surface through the boundary layer and into the bulk fluid. And in this case, which is typically referred to as equimolar counterdiffusion, the net velocity of all components traveling in the gas phase is 0, and so Vz star is equal to 0. If that stoichiometric coefficient is not equal to 1, then the molar average velocity in the gas phase can be either greater than or less than 0, depending upon the value of the stoichiometric coefficient. So now we have an expression for Vz star, and that's we will use that a bit later when we go about solving for the concentration profiles and the flux. So we turn now to the species continuity equation. The mass transfer, we only have in these sorts of problems where the mass transfer is driven by diffusion and chemical reaction at a surface, that is not driven by fluid mechanics like we saw in the falling film problem a couple lectures ago, then there's only really two relations that we have to, two differential equations that we have at our disposal. One is the mixture continuity equation, which we looked at above, and the other is the species continuity equation. And so we'll move on now to applying the species continuity equation to the gas phase. And so I'll write it for component A, and the general form is shown here in equation 9. There is no reaction in the gas phase. The reaction between A and B, or of A going to B, occurs at the catalytic surface. Remember the little hat on top of the RA means that this is the heterogeneous reaction rate, or the reaction rate of A at the catalytic surface. Without the hat, this means the reaction rate of A in the gas phase, which is 0 in this case. At steady state, the time derivative of 0 is 0, and so the continuity equation just reduces to the divergence. So the flux of A is equal to 0. We have one-dimensional diffusion, and so that divergence term reduces just to the spatial derivative of the flux of A in the z direction is equal to 0, and that just means that the flux of A in that gas boundary layer around this catalytic surface is constant. And you can go through similar logic for components B and C. I won't belabor that here, but you get to exactly the same result. That is that the derivatives of the flux of B and C with respect to Z are equal to 0. And this means that the fluxes of A, B, and C are all constant throughout the gas film, and that's the domain over which we're solving this problem. Now, in this case, we have an ideal gas mixture with no pressure gradients. There are no magnetic or electrical species-specific body forces, no ions involved. The system is at constant temperature, so there are no thermal diffusion effects, and it's in steady state. And so this is an ideal case to apply the Maxwell-Stefan equations. And so we go to the Maxwell-Stefan equations, and I've written them in I've written the Maxwell-Stefan equation for two of the components. You could in fact write this for all three components, A, B, and C, but in fact those three relationships are not independent, because the mole fraction of A plus that of B plus that of C has to sum to 1. So only two of these mass balances are actually independent of each other. And so I've written them Maxwell-Stefan equation for one of the reactive species. I picked A. You could just as well have written that for B if you wished. And also I've written it for the inert case. Now, we can get some relationships between the fluxes of A, B, and C by going to the species jump mass balance at the gas catalytic surface interface. And so I've written those relationships shown here. The overall jump mass balance, which we applied earlier, is just the sum of these three species-specific jump mass balances or interfacial balances at the surface. The interface is not moving, and so the terms involving the interfacial velocity u are all equal to 0. Component C does not undergo chemical reaction, so its reaction rate term is 0 at the surface. There's no gas of any species dissolved in the catalytic surface, so which would be in phase 1 of the picture shown here. So those concentrations of A, B, and C are equal to 0. The product of the concentration of a component times its velocity is by definition the molar flux of that component, and so I can write these terms Ca times Va in the gas phase, or Va superscript 2. I can write that as N sub A. Likewise, I can write the same thing for the flux of B and for the flux of C. And we find that the flux of C is equal to 0 at steady state, as it must be for an inert, and the fluxes of A and B are coupled by the reaction stoichiometry, and that is as A is converted to B, this sets the ratio of the fluxes of A to B. In the case of a stoichiometric coefficient of 1, that is n, lowercase n is equal to 1, that means A, just one molecule of A goes to one molecule of B, then we would find that the fluxes of A and B are equal and opposite to each other, as they would have to be. We know that these fluxes don't change as we go through the gas phase Z, and so that leaves us with the expressions that are boxed here at the bottom of the page for the fluxes throughout the gas phase. Then we can take these relationships, that is that the flux of C is 0 and that the flux of A and B are related to one another through this relationship involving a stoichiometry. We can plug those back into the Maxwell-Stefan equations, and I'll after doing that, I'll work on equation 20 first. This is the one involving the inert, and the reason for that is that it involves only diffusion coefficients of A through C, of B through C, the mole fraction of C, and the flux of A and the stoichiometric coefficient N. Now these diffusion coefficients will be, to a very good approximation, constant. The flux of A we know is constant from the analysis above, and the stoichiometric coefficient, of course, is a constant. The total molar concentration C is a constant because we're at constant temperature and pressure. Remember, C is pressure divided by R times T. And so if I look at this carefully, it basically reduces to a differential equation where it's dx c dz is equal to a constant times xc. And so that's why I want to pick this one out and work on it first. It's a bit easier, and then once I have an expression for xc, I can put that into equation 19 here and also here, and then solve for xa. And once I have xa and xc, then I can get the mole fraction of B as just 1 minus XA minus XC if I wish. So again, we come to equation 20 and work on this one first. We can algebraically rewrite it as shown here in equation 22, and I'll, just to save a little bit of writing, I'll write this grouping, constant grouping of terms on the right hand side as a new variable alpha, and that's just to save me from having to write this constant over and over. What you can see, though, immediately from this is that whether the concentration of A increases as you go towards the surface or decreases depends upon the ratio of the diffusion coefficient and the stoichiometric coefficients. So we can integrate this equation by applying the boundary conditions that at the edge of the boundary layer the concentration of C has its bulk value, and the result is shown here. It's just a simple exponential dependence on position in the boundary layer, and where the term alpha is given by the grouping of terms here up in equation 22. And so we can take this result and put it back into equation 19 and use the concentration dependence of xc as a function of z to integrate the equation with the boundary condition that at z equals 0, the concentration of A, or the mole fraction of A, is equal to its value in the bulk stream surrounding this catalytic surface. And the results of the integration are shown here. I'm not going to belabor this. There's some algebra that goes into it, but you can see hopefully where the how this goes. And the result, this particular result, is valid for all cases where the stoichiometric coefficient is not equal to 1. You can see that in the case where the stoichiometric coefficient were equal to 1, that is, the simple reaction A goes to B, then the result that's shown here would not work mathematically. And what's happened is in making this integration, we've divided by n-1, and that has caused this expression now to blow up if in the case of stoichiometric coefficient equals 1. You can come back and insert n equals 1 at this stage in equation 26, and then integrate that as a separate case to get the unimolecular expression for a concentration profile. So we calculate the flux by applying the boundary condition that at the surface of the catalytic surface the reaction is instantaneously fast, that is at z equal to delta, xa is equal to 0. And so if we apply that that boundary condition, we get essentially an implicit expression for the gas flux. It involves these parameters alpha and gamma, which are defined up here in equation 29. To get a little more insight into the structure of this solution, we consider the unimolecular case, and now we go back to our differential equation for Xa, plugging in n equals 1, and we can integrate this expression to get the expression shown in 32. And note that if there is no inert present, in other words, if this gas mixture were only a binary mixture of A and B, then this term involving Xc would go away, and you'd have essentially a linear concentration profile for component A in that boundary layer, and the extent to which that is not linear depends upon essentially the presence of the inert species. We can also solve for the flux by imposing the boundary condition that z equals delta, xa is equal to 0, and so we get the flux expression shown in equation 35. And this is for the case where we have the stoichiometric coefficient n is equal to 1. And again, you can see that if there is no inert present, this second term in brackets goes away, and the flux of A is then given by the very simple result that it is the diffusion coefficient of A through B times the concentration of A at the edge of the boundary layer divided by the thickness of the boundary layer, and that is exactly the result you'd get if you had integrated the simplest form of Fick's law for a binary case, and that is that the flux was equal to minus d times dc dx and integrated that for constant diffusion coefficient, or excuse me, minus d times dc dz in this case, and integrated that for constant diffusion coefficient, taking as boundary conditions that at z equals 0, xa is equal to xa0, and at z equal delta, xa is equal to 0. So this reduces to that simple case with when there's no inert present. Okay, so that's one look at it, at how a third component influences the transport and concentration profiles of species that are to other species that are undergoing chemical reaction. We're going to come back to this problem in a moment and look at it from a slightly different point of view, but I'll let it go for now, and want to move on to an explicit numerical solution for a Stefan diffusion tube problem. We looked at this problem earlier using shell balances, and before we developed the machinery of the general continuity and species continuity equations. And so now we'd like to come back and look at it again and essentially reanalyze it using the more general machinery of the continuity equation and the species continuity equation, as well as the jump mass balances, the tools that we've developed here in Chapter 19. The results that we get will not be different from what we obtained earlier, but I'll just show you how to get to them using this more general machinery, and we'll also do specific calculations for a case involving evaporation of water from this tube. Now we're going to pick a scenario here that is probably not one in which you would design a Stefan tube to measure diffusion coefficients. So we're going to pick a tube that's 3 meters high, and it's got 15 centimeters of water down in the bottom of it. It's at 21 degrees C and 1 atmosphere pressure. And the reason that's important is because that sets the vapor pressure of water at 21 degrees C is 19 millimeters of mercury, and the mole fraction of water in the gas phase just above the liquid water is given by Raoult's law, is just the vapor pressure of water over the total pressure, so it's about 2.5 mole percent. And so that means that the air is about 97.5 mole percent here, and the water vapor is 2.5 mole percent. This is a case where we're going to use the concept of effective binary diffusion coefficients. Remember we talked earlier about a component like air being composed of many different species, and we can simplify that down to a pseudo-binary case in the limit where only one component, in this case the water, is really moving, and all the other components are either stationary or move with the same velocity, so the oxygen, the nitrogen, the CO2, and so forth. Those components in air are essentially moving only when water evaporates from the liquid here that requires more air to come into this tube to maintain the pressure at 1 atmosphere. And so all of the air components essentially move together as the liquid level in this tube falls. And we'll consider a case where up here at the very top of the Stefan tube we have a flow of air such that it maintains the mole fraction of water equal to 0. And so we're going to ask how long it will take the water to evaporate out of this tube. And it turns out it's going to be a surprisingly long period of time, and that's basically because the tube is quite tall, and we don't allow any sort of convective mixing inside the tube, and diffusion alone under these circumstances, diffusion of water through that gas phase is actually a very slow process, as we're about to see. Okay, that sets the basic conditions of the problem, and we'll start out again. The problem-solving procedure that I'm showing you in the previous problem and this one and the next one is what I've found to be the most convenient way of starting and working through these problems. And so we always start with the mixture continuity equation. There's no chemical reaction, and so we set that term equal to 0. There's no reason in this case not to assume ideal gas behavior. There will be a slight hydrostatic pressure gradient from one end of this tube to another, but it's really not enough to change that molar concentration of gas significantly. So we'll take the molar concentration of the gas to be constant, and the mixture continuity equation can then be written as shown here. We've moved the molar concentration outside the derivative and gotten rid of the reaction term since there's no chemical reaction. We're going to, as we solve the Stefan diffusion tube problem earlier, we're going to assume quasi-steady state, and that means, or pseudo-steady state, and that means that the time scale for the evaporation, that is to reduce the liquid level in the tube, is much greater than the time scale to establish a steady state concentration profile of the components in the gas phase. And I'm going to assert to you for the moment that a reasonable estimate of the time scale to establish a steady state gas concentration profile throughout the gas phase of this reaction, of this Stefan tube, that the time scale to establish that steady state should go like the square of the gas phase diffusion length, which I'm calling delta. That'll be 3 meters in this case. It should go like the square of delta divided by the diffusion coefficient, in this case of water in air. Now, we're going to come back in, I guess, probably the next lecture, and I'll show you how to derive this criteria from first principles. For now, I'm going to ask you to accept it that the time scale to establish that concentration gradient in the gas phase is the square of the diffusion path length divided by the diffusion coefficient of water in air. We plug the numbers in, and that comes out to be about a little over 4 days. And that may seem like a long time, but it's important to remember that this is only this time scale is not to be taken relative to human time scale for being in the lab or doing something like that. It's to be taken relative to the time scale to completely evaporate the water out of that tube, and it's going to turn out that this is just a minuscule amount of the time that it takes to actually evaporate all of the water, and it is that large separation in time scales. This is going to turn out to be essentially instantaneously fast relative to the time scale to evaporate all the water out of the tube. And the large separation in those two time scales is what allows us to make this pseudo-steady state approximation and set the concentration, the time derivative of the concentration equal to 0 or so close to 0 that it's effectively negligible. And this leaves us with the result that the divergence of the molar average velocity in the gas phase is equal to 0. If the diffusion is one-dimensional, this means that the molar average velocity has a constant value. And again, like in the previous problem, what we get out of the mixture continuity equation is we get some information about what this molar average, the value of this molar average velocity is, or how it depends on space and time, and we find out that that it's constant. To fix the value of that constant, we have to go to the mixture jump mass balance, exactly the way we did in the previous problem. So we start with the mixture continuity equation to see how that average velocity changes in space and time, and then we go to the mixture jump mass balance to get more information about an explicit value for that molar average velocity. And this situation is going to be somewhat different from the catalytic surface jump mass balance in the sense there's no chemical reaction, and now the interface is going to be moving. The liquid vapor interface will be moving in the negative y direction. As the water evaporates, that liquid vapor interface is going to fall, and that means that U in this case does have a finite and in this case negative value. So we write the mixture jump mass balance as we have before, assuming no chemical reaction, so there's no reactive term on the right hand side, and then we apply the standard definition, writing this term out on one side in the gas phase and setting it equal to its corresponding term in the liquid phase. We assume that the liquid has no net motion in the y direction. I've said this is the condition that the liquid is quiescent, and so that means that in the liquid phase, phase 2, there is no net motion of the liquid itself in the y direction. So this term goes to 0. We can then reorganize the jump mass balance to give us the following result, and that is that the value of the gas phase velocity in the y direction is related to the rate at which that liquid vapor interface decreases, uy, and the coefficient that relates these two velocities are these concentrations. Let's have a closer look at that. So C1 is the concentration of in the of the mixture in the gas phase. C2 is the concentration of the mixture in the liquid phase. So C1 we get just as from P divided by R times T. It's on the order of 10 to the minus 5 moles per cc. That's gas phase molar concentrations. C2 is the concentration, mixture concentration in the liquid phase, and this is essentially this liquid phase is essentially pure water. There will be a little bit of air gases dissolved in there, but they're at mole fractions that are like 10 to the minus 6 of parts per million. And so we can effectively take the concentration in the liquid phase to be that of pure water at ambient conditions. That's about 1 gram per cc, and then this is the molecular weight of water. And so what you can see immediately is in this bracketed term, the gas phase concentration C1 is orders of magnitude less than the liquid phase concentration C2, and so we can use that fact to simplify this term in brackets as shown here, and then we can plug the numbers in and get the result that's shown at the bottom of the page. And this is giving us a result that we discussed in class intuitively, and that is that the gas phase velocity is opposite the velocity of the liquid vapor interface. That is, as the water evaporates, that liquid vapor interface decreases, and this gives rise to a positive gas phase velocity. Essentially, uy is negative as the liquid phase drops as the evaporation occurs. It also tells us the factor that relates the gas phase velocity and the drop in the liquid level, and that factor in this particular case is 1340. Now what that means is, if the liquid vapor interface is decreasing at a certain rate in, let's say, centimeters per second, then as you convert that liquid to gas, the gas has a much lower density, and so in order to move that amount of material away from that gas-liquid interface in the gas phase velocity has to be 1,300 times higher, essentially, than the rate at which the liquid level drops, and that's simply because of the vast difference in concentration of material in the liquid phase and in the gas phase. So that, and we discussed this result as from an intuitive point of view in class, and now you can see it quantitatively. And so now we have a relationship between the molar average velocity and the velocity at which the liquid vapor interface drops, u sub y, and that's all that we get out of our overall continuity and overall jump mass balance. And so now we turn to the species jump mass balance, and we're going to focus on water because this is the component that's evaporating or diffusing in this case. And we write the species jump mass balance again in the limit of no chemical reaction. We expand or write out these terms explicitly as we did earlier, with the assumption that the liquid water is not moving in the y direction, or it's quiescent, and this will give us an expression basically for the flux of water at the liquid vapor interface, and it's related to the concentration of water in the liquid phase times the interface velocity. And this is under the assumption again that the concentration of water in the liquid phase is much greater than it is in the gas phase. And this result, I hope, will make intuitive sense to you as well, that all of the water flux in the gas phase is coming about because water is evaporating from the liquid phase, and essentially the rate of evaporation in terms of the change in the height of that liquid phase is uy, and if you multiply that times the concentration of the water in the liquid phase, this grouping of terms is essentially the flux of water away from the liquid, and that has to be equal to, at least in magnitude, to the flux of water in the vertical direction. We can also apply the jump mass balance to the air phase, and here we assume that essentially there's no air dissolved in the water. There will be parts per million level of air gases dissolved in water, but they will not be enough to affect the outcome of this calculation. And what you find from that jump mass balance is the flux of the air is equal to the concentration of air in the gas phase, and we've said we can calculate that basically as P divided by RT times the mole fraction of air in the gas phase, and at that interface the mole fraction of air in the gas phase is 97.5%, because we calculated earlier that there was 2.5% water right at the liquid vapor interface in the gas phase. And what this says then is that the flux of air is equal to the rate at which the interface, liquid vapor interface, decreases or moves times the concentration of air. And essentially this gives the notion that as the liquid evaporates and the liquid level falls, then you have a flux of air into this tube that is just enough to offset that the distance by which or the amount by which this liquid level has fallen, and basically that's required to keep the pressure constant in the tube. And so again, you can relate the flux of air to the interface velocity, liquid vapor interface velocity, or the rate of evaporation. And because the air and water fluxes are both related to this interface velocity, we can relate them one to the other as shown here, and you get a relationship between the air flux and the water flux. There's a negative sign there, meaning that the air flux and water flux are counter to each other. In other words, as the water evaporates upward, there has to be some air flowing downward to take its place. And based on these concentrations, the concentration of air in the gas phase divided by the concentration of water in the liquid phase, that number is going to be a number that is very much less than 1. And so, as you would expect, the flux of air is much less than the flux of water. All the air has to do is take the place of liquid that's evaporated. The water is expanded by more than 1,000 times on going from the liquid to the gas phase, and so its flux in the gas phase has to be way greater than that of the air, which is just displacing the liquid in this tube. And so that point is being made more explicitly here, and essentially what you find is that the flux of air has to be much less than that of water, and so for all intents and purposes we can set the flux of air to 0 in the subsequent analysis that we're going to do. So now we turn to species continuity equation, and we'll work on water, since that's the component that we're interested in monitoring here. There's no chemical reaction, so we can get rid of the reaction term. We're treating this problem in the limit of a quasi-steady state, or it's what's often called pseudo-steady state. And so the time derivative goes away, and in that limit we get that the divergence of the flux of the water is equal to 0. Since we have one-dimensional diffusion, that result simplifies to the result shown here, and this further implies that the flux of water in the y direction is equal to a constant. We then, for our flux model, we insert Fick's law and the appropriate convective or frame of reference contribution. This is exactly the flux law that we've been using all along for binary systems, and we've made the approximation here that the flux of air is much less than that of water, and so we neglect the air flux in this balance on in this expression for the flux of water, and that result then simplifies as shown here. We can integrate the flux expression over the gas phase length of the tube, that is starting from the liquid gas interface, which is y equals 0, and going up to the top of the tube, which is y equal to delta, and we have these corresponding concentrations or mole fractions of water at the liquid vapor interface and then at the top of the tube respectively. We've argued already that the total molar concentration is constant, so that comes out of the integral. The effective diffusion coefficient is really very weakly dependent on concentration, so that can come out of the integral, and we get the simple result that's shown here. And so we can calculate the gas flux, the water vapor flux, using the boxed expression here on the top of page 7. And so we'll first calculate the flux at the beginning of this experiment, when delta is equal to 3 meters. As the evaporation goes on, the distance delta will actually increase to 3 meters, all the way up to 3 meters and 15 centimeters at the end of the experiment, when all of the water is evaporated, because they have 15 centimeters of water and 3 meters of air in the tube above it. So the total tube length is 3.15 meters. And so we'll calculate the flux initially, where when the gas phase diffusion length is 3 meters, that's its shortest value, and so the flux will be highest, and that'll give us the shortest time for evaporating all of the water. So it gives us a conservative estimate of how long it takes to evaporate the water. It's actually take a little bit longer than the value we're going to calculate here. So we put in numbers for the flux of water because we know the molar concentration. We calculated that above. We know the diffusion coefficient of water and air. We know the gas phase distance, 3 3 meters, and we know the concentration or mole fraction of water at the gas-liquid interface. It's 2.5 mole percent, and so that gives us an explicit expression for the flux of water. We can use the jump mass balance then to calculate the rate at which the liquid-vapor interface goes down, and it's on the order of fractions of a micron per second. And the time to evaporate then 15 centimeters of water will be the 15 centimeters of water divided by the rate at which the water level is decreasing with time, and it gives a result that is somewhat over 30 years. And so this is the proper time to compare that 4.25 days to that we calculated earlier, which was the time to establish concentration, steady state concentration profile in the gas phase, is on the order of 4 days. The time to evaporate the water just by diffusion out of this tube is on the order of decades. And so by that measure, there's an enormous separation of these two time scales. The time scale to establish the steady state concentration profile in the gas phase versus the time scale for the evaporation to actually occur. And it is this separation of time scales that allows us to make that pseudo-steady state approximation that the gas phase concentration profile is effectively constant and changes so slowly with time that we can use that steady state approximation of that gas phase concentration profile to ultimately estimate the non-steady state behavior of the system as a whole. Now we can come in and so that's the point that's made here at the top of the page. If you wish, you can calculate the concentration profile by integrating the water continuity equation from the liquid vapor surface up to some arbitrary distance y instead of going all the way to the top of the tube. And if you do that, you will find the concentration profile that's shown here. And you can also calculate the interface velocity is shown here, and the final result of that is given at the bottom of this page. I'm not going to belabor further calculations of the interface velocity, but just simply show you how it's related to the diffusion coefficients and the concentrations and so forth. The last little bit of this is that we can carry out the macroscopic mass balance that we did in our previous analysis of the Stefan tube, and use that to get a more accurate estimate of the time over which the evaporation will occur. And so delta is the gas phase height in this tube, L is the overall tube length, and L minus delta will be the liquid level in the tube. Now, this is not drawn to scale based on our previous tube where delta is 3 meters and L minus delta is 15 centimeters. But the principle of applying this mass balance will be the same. And so we write an overall mass balance on the water that is in the tube. And so the time rate of change of the total amount of water, total mass of water, this is in the liquid phase, has to be equal to the water flux, and this is in molar units, so we multiply by the molecular weight and times the cross-sectional area. So this term will give us the net rate at which water is evaporating from this tube. The minus sign accounts for the fact that the amount of mass of water, that the flux is a positive number in our case, and the minus sign accounts for the fact that the total mass of water is decreasing over time. And so we can plug in our expression for the flux and integrate this expression to get a result that's very similar to what we saw in our earlier analysis of the Stefan tube problem. This is basically an expression for the gas phase height in this tube delta, and how that changes with time. We can calculate the mass of liquid in the tube as just the density of water times the volume of water, and the volume of water in the tube is just the cross-sectional area times L minus delta. So L minus delta times the cross-sectional area of the tube times gives us the volume of water, and then multiply that times the density, and we get the mass of water in the tube. We can plug in this expression for the gas phase height, and the time to evaporate all of the liquid in the column occurs when this gas phase height is just equal to the total tube length L. So when delta becomes equal to L, then all of the liquid in the column will have been evaporated, and if you plug in numbers, you get about 31.6 years. So our first cut analysis, where we just calculated the maximum rate of evaporation, which is the rate of evaporation at the beginning of this experiment when delta was equal to 3 meters. If we just use that flux to calculate the time to evaporation, we got a value of about 31 years. We get somewhat longer value here, and that's just accounting for the fact that as the evaporation goes on, the gas phase distance here increases a bit, and that slows down the mass flux with time, and so you get just a slightly longer diffusion time. And so I think we're getting towards a good stopping point for this particular lecture. I would like to point out that I put on the notes for you an article by Steve Whitaker, which has a more in-depth analysis of the Stefan diffusion tube. I'm not going to go over it in class, but it accounts for some effects that we have not taken into account. So, for example, we have done this problem in the limit where we assume that the gas phase velocity profile is essentially flat. This is getting at the fact that we're treating it as a one-dimensional diffusion problem and not allowing for variations in the direction that's perpendicular to the direction of net transport. You'll realize, from fluid mechanics that this flat velocity profile has to be an approximation, and so in here, Whitaker walks through the analysis of in more detail about cases under which the flat velocity profile is an adequate approximation to the parabolic velocity profile that you should expect in these kinds of systems. And essentially it turns out that for all cases that are of practical importance to us, the analysis that we've done which is the standard analysis of a Stefan tube, is adequate. But for those of you who'd like to learn a little bit more about how to include these types of effects in such an analysis and to estimate the order of magnitude of their effects, this is a very nice article by Steve Whitaker. All right, I'm going to stop the lecture there, and we'll pick it up again next time, starting with one more example of using Maxwell-Stefan approach to solving diffusion problems. Thank you.